Hello everyone, my name is Xiuheng Wang. I'm going to introduce our recent work on deep image fusion accounting for inter-image variability. Let's start with hyperspectral imaging. As you can see in this figure, hyperspectral images have a high spectral resolution. This property allows hyperspectral images to be successfully applied in many fields, such as remote sensing and medical science. Due to the hardware limitation of the hyperspectral imaging system, there is a trade-off in the spatial and spectral resolution. As a result, hyperspectral images contains hundreds of spectral bands. However, it with a low spectral resolution. On the other hand, multispectral images contain very few spectral bands, but with a high spatial resolution. Naturally, we can consider fusing these two kinds of images to recover high-resolution image with both high spectral and spatial resolution. Images acquired by different satellites or at different dates lead to different atmospheric conditions, illumination variations, and seasonal changes. These factors will cause inter-image variability between the acquired images. Before introducing our work, let's formulate the degradation model accounting for inter-image variability. From observation model, the hyperspectral image YH can be viewed as degradation of ZH in the spatial domain. The multispectral image Ym can be regarded as the spectral degradation of Zm. We can estimate ZH and Zm in the sense of the MAP principle by solving the following optimization problem. However, this is an ill-posed problem. We need to choose different regularizers to enforce the desired property of the output. In this work, we consider the following desirable property for the high-resolution images. First, the inter-image divergence between ZH and Zm should be smooth and sparse. Second, ZH and Zm should be similar with real-world hyperspectral images. We will write the optimization problem as following. The last regularization term enforces the smoothness and sparsity of inter-image variations, while the phi ZH and the phi Zm encode the spatial and spectral priors. To optimize the non-convex and the non-smooth term, we consider an iteratively reweighted update strategy. For fixed W, we compute ZH and Zm by solving the following optimization problem, and then we update the entries of W according to equation 6. In the following, we focus on solving the optimization problem in equation 5. By introducing two auxiliary variables, we can write a Lagrange function to decouple the data fidelity term and the regularization terms. And then we can minimize the Lagrange function with respect to all variables. The subproblems 8 and 9 can be solved by the CG algorithm. To solve the subproblem 10 and 11, we propose to use the red strategy to learn priors for hyperspectral images by CNN-based denoiser. In this step, there are three challenges needed to be considered. First, there is a limited amount of data available for training. Second, there is even greater lack of the labels. Third, the noise level of high-resolution images changes over iterations. For the limited amount of training data, we consider a lightweight network architecture. Two strategies are considered: dimensionality reduction and the separable convolution. Dimensional reduction allows us to rewrite high-resolution image V as QX. By denoising X rather than V, the number of the filter is decreased. On the other hand, separable convolution aims to compose a convolution filter into a depth-wise filter and a point-wise filter. It reduces the filter parameters. Totally, the network parameter can be significantly reduced with this ratio. To tackle the issue of the lack of labels, we propose to use training strategy that is both in unsupervised and zero-shot manners. Consider an observed noise image X generated by Z plus E. We can assume that if a CNN denoiser can recover Z from X, it can also recover X from X plus E. It allows us to train CNNs by minimizing the following L1 best. loss function. Since there are iter-image variations, we train two independent denoisers for VH and VM. Considering the noise level of VH and VM decreased over iterations, we adaptively update the theta H and theta M at each iterations. To make the algorithm faster, we train the CNS in the first iteration and fine-tune them in the remaining iterations. Now we test our method on real data to show its effectiveness. We consider these three image pairs with inter-image variability, and these two state-of-the-art methods to compare. From this table, we can see that our method achieves the best result in quantitative comparisons. The visual effects of the result are shown in this figure. It indicates that our method provides a spectral reconstruction closest to the ground truth. This figure illustrates the PSNR curves. Our method also achieved the best in all the spectral band. Thanks for your attention. More details can be found in our full paper by scanning this QR code.